student showcase. So if you give us something, get the latest and most fabulous students. Got a few bits of admin to run through as usual, before we move to our speakers. For our drills and fire is each just endorse the fact. To look through to so we're getting there with our program, but 2 talks left after this. We've got our away days were in Aberdeen next month, where we're going to look at the Scottish Avalanche Information Service, which is a really interesting talk. And then to finish off back here in March, investigating Dale, artificial intelligence, and some really big. Advertising reminder, everybody know this, anyone online as well. The advantages, many advantages. It's the point. We've got 2 speakers tonight. Thank you both for coming. So first up is Toby Jones. We're talking about correlation of wind and precipitation and the fact of the severity of European cyclones. So the investigation into the correlation between those. So, that is very good. So let's do this.
Okay, amazing. Thank you so much for having me.
You've still got your full PowerPoint on the Zoom call, yeah.
That's great. No.
Yes.
Yeah, sorry about that. Okay, we'll go again. Thank you very much for having me. So my name's Toby Jones. I'm a PhD student at the University of Exeter. And yes, as Greg said, the title is a bit of a mouthful. So I'm going to start with the question of how are yearly wind and rain windstorm losses related? And as that title is a bit of a mouthful, I think I'm going to start by putting the 1-word phrase there, or 2-word phrase, aggregate severity, and let's kind of pull apart what I'm going to mean by that. So, what is aggregate severity? So, we're thinking about loss, damage, risk, but we're thinking about that over the course of a year. So, in this case, our total loss in a period is just going to be the sum Sx, which is our loss x1, all the way up to our loss xn, if we see n events in a year. And this sum is driven by those number of events we see in a year, and it's also driven by the intensity of those events. And as you can see kind of on the figure, it's got quite a large variation, and quite kind of fictional data. You see 2003, we only had 3 events, but it was kind of quite a large long year. And the reason kind of behind thinking about aggregate severity and the real motivation behind this talk is aggregate severity, the calculation of that, and kind of using that time frame is how insurance premiums are calculated. So we want to be thinking about our kind of risk over the course of the year, our severity over the course of the year, rather than an individual event. So that's how these insurance premiums and reinsurance contracts and everything, are all kind of worked out. So, aggregate severity ticked off. Second question, why windstorms? Well, windstorms are the main driver for extreme wind and heavy precipitation in Europe. Most of the time, you've got a windy day or you need to get your umbrella when you leave the house. That's because you've got a storm coming through. And it might not be a named storm, it can just be a low pressure system, but it's still a storm that's bringing wind and rain to Europe. And the interesting thing is that because this one system brings two hazards, from an insurance point of view, there's two aggregate severities that they need to be thinking about. And these two aggregate severities are driven by one event, or many events, but one thing, storms, going to drive these two events. And we don't really know what that relationship is. So current literature has looked at the wind-rain relationship for storms, but it's not thought about that yearly timescale. And kind of what we'd expect, and hold on to this because we're going to, well, the purpose of the talk is to try and find out what's going on. So we kind of expect to see more storms, then we're going to have more wind and rain losses, and then we're going to get these larger totals. So if we have a year with more storms, we're going to get larger totals. A year with less storms, we're going to get smaller totals. So our relationship, our kind of correlation, we should kind of expect a positive kind of trend. So this kind of leads us to our point. What is this relationship? And can we kind of model it to kind of understand what's driving it? So let's kind of dive right in. And actually, I suppose I probably should mention on right. Actually, so the 4 storms we've had this season are a really good example of why storms are this kind of dual peril. Ashley Burke, Conor Mandara, all have brought wind, rain, not necessarily at the same time, but different locations. And kind of real good example of why investigation into kind of this kind of relationship is really important. So let's think about how we can model this. So it'd be really, really good is if we're thinking about insurance losses and stuff like that, to have like a high resolution insurance loss data set, split into wind and rain damage that occurs from storms. But we don't have that. So instead, what we're going to do is we're going to focus on the hazard, as in focusing on wind speed and rainfall, and just use severity indices to translate that to kind of a proxy measure of loss. So when we have these severity indices for each event, we can then add up all of the total severity for over the year, and that'll give us our aggregate severity index, which is going to be a proxy measure for our aggregate severity. So in short, what we're going to do is we're going to use wind speed and rainfall as a measure of our aggregate loss. And just a little bit more on kind of severity indices and the ones we're going to use. So there's a really good paper in 2003, which is where they designed a severity index for wind speed. It's the Carroll Aldrich paper. So those in windstorms kind of they're pretty well known, and it's a bit more complex. So it takes the 90th percentile of wind speed, it takes the exceeds of that, cubes it. But like it's a really, really good estimate for insurance lines. And the problem is the same thing doesn't really exist for precipitation. While wind is kind of a really easy metric to think about damage, it's windy, your roof tiles are going to go off your house. Rain's a little bit more complex. If you have heavy rain, it might not cause flooding. You could have relatively light rain to a degree, and that could cause damage. It depends on the kind of precursor conditions, depends where you are, if you're at the top of the hill or by a river, if there's storm surge, all of these factors come into play for flooding. So precipitation kind of severity index relating that to loss is. So what we're going to do, because there's no perfect kind of one size fits all for both, we're just going to use a really simple model. A simple model, probably best thought about with this image here. So all of our events we're going to take some sort of threshold, UX say, and we're just going to take the exceedance of the value above that threshold. So as I said, it gives us that focus on the hazard of our extremes, but it also is kind of a lot more easier to understand than say kind of cubing in and taking away stuff, and it's just so much easier to think about. We're just going to take the exceedance. So we will have a threshold for our wind and a threshold for our rain, and that'll give us our severity. So how are we going to get a aggregate severity index from storms? It's all very well and good thinking, oh, we need wind speed and rainfall data, but we need to make sure that this wind speed and rainfall data comes from storms. So this is our kind of approach of getting our aggregate severity data. So step one, we use 0.5, and we're going to use a storm tracking algorithm called TRACK to create what's the black line. This uses relative vorticity at 850 millibars to take the storm track at hourly intervals, and we're doing that for our entire data set, so from 1940 to 2020. And then we're going to think about, okay, which grid points of area 5 is this storm track influencing? Because we might have multiple storms occurring at once. We don't want to associate 2 different grid points or 1 grid point with 2 different storms. So we're going to take our red circle, which is a 5-degree radius. That's commonly used. So that's going to say if the grid point's within the radius, we're going to associate that wind speed and rainfall value to that storm. And then that takes us to step 2. With all the wind speed and rainfall data that we have over all the time steps of the lifetime of the storm, for the wind speed, which is top panel, panel A, we're going to take the maximum wind speed value. We're going to say that is the severity of the storm. And we're using 10 meter per second gust speeds here. And then for precipitation, it's a little bit easier. For that grid point, we're just going to take total precipitation that occurs at that grid point as our severity of the storm. And then, as we just see, we're going to use our simple severity index. You can see mathematically it's written out there. So the exceeds above the threshold, and that's going to be our severity for our wind speed and our rainfall. And then we can take all of our severity indices, add them up for all of the storms that occur in the year, and then we're going to get our aggregate severity index. So, important to note that this aggregate severity index is dependent on the threshold we choose. Because if it's below the threshold of 0, it's not adding anything to the sum, to the yearly loss. So the choice of threshold is important. And you can see that here. This is an example. What we've done is taken all the grid points over France, we've aggregated them. So we've got kind of a time series of aggregate severity. And the yellow line is our SX, that's our wind aggregate severity. Our blue dashed line is our rain aggregate severity. The 3 panels represent 3 different choices of threshold combination. So our top panel, we've got where we're doing almost no thresholding at all. And then our bottom panel is where we're taking 20 meters per second and 20 millimeters, which 20 meters per second commonly used as a wind speed damage threshold. And you can see that kind of around 2010, the top panels, the wind speed and the rainfall severities kind of follow each other quite well. And then you can see on the bottom panel, they kind of seem to be quite different. So let's kind of cast our mind back to one of those first slides where I said more storms is more wind and rain losses, so we expect a positive relationship. Well, let's actually see what the correlation is here. So we can see that on our top panel, we actually have quite a good correlation value. So correlation is between -1 and 1. 1 is a perfect linear correlation for a positive relationship. -1 is a perfect negative correlation, and 0 is kind of, they're not really related at all. But when we get to our extremes, what we see is we see this kind of negative or near 0 kind of relationship occur. And I'll be really honest, when me and my supervisor first saw this, we were quite surprised. Because we were going on this idea, more storms, more losses, positive relation. And we can plot what this looks like. So this is what, in this case, we've aggregated for all of France, but we can pull it out and look at the correlation for all of our grid points. So our top panel, we've got that positive correlation occurring. Our bottom panel, we've got kind of gap dots of negative correlation. And I'm going to draw your attention to the two boxes. So box I over the Azores, box II over France. And you can see how they kind of behave differently. And the reason for this is to do with how we've chosen our thresholds. Because storms, they form over the west of the Atlantic, they gain strength, they've got a source of moisture over the ocean, and when over the ocean, they're going to be a lot stronger than when they're hitting land, they're slowing down, they haven't got a source of moisture. And so actually, although we're using these fixed thresholds here, it actually makes a bit more sense to use a percentile-based threshold. So if we go to a percentile-based threshold, we say 98th percentile, we're choosing 2% of storms to be extreme for that wind speed and rainfall. So are we going to see a similar pattern? Are we going to see this kind of land-sea contrast in kind of positive, negative correlation over the ocean for our extremes? Fortunately, to make life a little bit easier, we're kind of seeing more of a similar pattern, but over the ocean. So we still get this positive to near zero negative transition as we go from no threshold with our 0 percentile to our extreme storm with 98th percentile. But it's kind of more spread. So we've kind of got similar behavior occurring over the ocean and over land. So it can kind of make a bit more sense to use percentile-based thresholds. So we're going to kind of stick with this idea from now on. So at the start of the talk, I said we've got two questions. What is the correlation? And once we work out what the correlation is, can we model it? But we've kind of then thrown in our curveball in here because the correlation is not just one thing, it's dependent on our thresholds we've found. So we need to find a framework. Apologies, it's going to be a bit of maths, but I'll try and not dwell on it too much. You're going to have a framework that is going to model our correlation, but based on the different thresholds. So what we're going to do is we're going to assume that our frequency and severity of events are random variables. We're going to, from that, we can then say that statistically we can derive the equations to get some sort of expression and framework for what the correlation should be based on all of the assumptions between frequency and intensity that we specify. And if we have a kind of really good match between that correlation plot that I just showed you and a kind of framework estimate that we're going to use frequency and intensity to get, if they match really, really well, then we can take our framework and we can pull it apart and we can understand why the correlation is changing, what's causing this change of threshold, what factors are at play. Because we know that the aggregate severities of wind and rain are just influenced by the number of events we see and the intensities of wind and intensity of rain. So that's the idea, and very much easier said than done. And the bulk of my PhD has been coming up with frameworks that are simple yet match the correlation. But this is what we've got so far. So we're going to assume a couple of things about these random variables that we've described. Mostly that they can't be negative, which makes sense. We can't have -1 storms in a year. We can't have -5 meters per second wind speed. And these x and y, so our wind speed and our rainfall random variables, they're going to have some sort of correlation themselves. They're going to be related. But what we're also going to do is we're going to introduce another variable, z. Now, this variable z is just a latent variable. It's not going to take any value, but statistically, we're going to think about it that it's fixed for each year. So z is going to vary between years, but given year it's fixed. And when we're then deriving our expression for what the correlation is, that's going to mean that we can condition on the variables, and it's going to allow us to split apart variables that we wouldn't have been able to do. And you can think about it being fixed is this idea that Z is this kind of mimicking of like the mean state of the North Atlantic Oscillation, or it's an active or inactive storm season. There's some sort of kind of variables influencing, but remember it's fixed each year. Again, so I did warn you there was going to be some math coming up. So we've got two random sums, and to get correlation, what we need is the covariance and the variance of these random sums. And we can find the variance. The variance is dependent on our means, which is the E expectation, and it's dependent on the variance of our frequency and our intensity. So our frequency is our X, sorry, our frequency is our lambda, and our intensity is our X. And so our lambda is just the mean number of storms we see in a year. And so that also is true for covariance. It's just dependent on the mean, the variance of our frequency and intensity. But we also have this other parameter, which is phi. Excuse me. And the phi parameter is, for those not familiar, a measure of storm clustering. So it's called the dispersion statistic. And when phi is 0, we get really, really regular behavior. So we would see maybe the storm every 2 weeks. When phi is 1, we see this kind of random behavior. But where it's interesting is when phi is greater than 1. So when phi is greater than 1 here, what we can see is we see these clusters of events occurring. And a good, really good example is Dudley, Eunice, Franklin. Those 3 storms that we had in a week about a few years ago. Really, really good example of storm clustering. And this actually is a figure of storms that have been tracked. And the bottom panel is where it's less clustered, further south, and the top panel further north is London, I believe, where they're more clustered. And so it's just interesting that this kind of cropped up in our relationship between the two aggregate severities. So let's look at the framework. So remembering that it's just covariance and variance give us our result. So we can kind of simplify it a little bit. And I want to think about the framework as being just A plus B plus C. And A is going to be our clustering coefficient. We can think about that as a measure of how our storms are occurring in time. B is going to be our within year relationship. So it's how X and Y, our intensities, are related in each year. And then C is going to be our between year relationship. So how is like a mean of X and our mean of Y related as we change. So I'm going to show you how well we perform with those percentile-based thresholds. So on the left, we have the sample correlation. And on the right, we have our framework estimate. Now, I know it's not matching perfectly, but remembering how relatively simple, all we're taking is the frequency intensity, and we're managing to pretty much capture not only the negative to positive to negative transition of the increased threshold, but we also at the 80th percentile are capturing that where that transition is occurring first is over land. And we're only kind of consistently about 0.1, 0.2 slightly lower than the actual correlation value. And that's partly because we're not making our framework very complex. We're trying to think about, let's only assume a few things. Let's really kind of make it simple, and then we can put it apart and understand it better. Now, I appreciate trying to assess like how well this is performed. It's actually quite tough because it's quite noisy. So what we're going to do is we can, like we did for that France point, France with the time series I showed right at the start, we can split Europe into 7 regions, and we just use the ones that define by Separino, that's how I remember before. See them there. And we're going to treat each one like a big grid cell. So for every storm, the UK will have a wind speed severity and a rainfall severity. And we can recalculate the frequency, go through all of those steps we did before, but then what we can then do is calculate or estimate for the correlation with our framework at different thresholds. So these figures are very similar, but we're just now showing you different percentiles on the x-axis. So you can see all of the regions, as we had before, we're ever so slightly off, but we're matching the shape really, really well. And this is kind of a pretty good enough match to kind of understand what that correlation is doing. Because we know that there's not going to be that much difference that's really kind of driving this behavior. So let's kind of zoom in so we can see kind of one area better. We've got the GBIE region. So our red is our sample correlation. Our blue dashed line is our framework. The x-axis is the percentile threshold for the severity index we're using. The y-axis is the correlation. So you can see as we increase the percentile, so as we only think about more and more extreme storms, correlation decreases to being near zero or negative. Now, the black lines behind, so the solid black line is that event clustering term that I was talking about. You can see that that's always positive, no matter what the threshold is. The within year term, which is the dashed line, is always negative. So we're always going to get kind of storms that, as we get more and more extreme, they're always going to be either windy or wet. We're always kind of getting this kind of negative correlation. But the thing that seems to really, really control this behavior from positive to negative is this between year relationship C. And that is dependent on the threshold. You can see low threshold positive, and as it gets bigger, the threshold gets bigger, then C goes negative. And so we kind of get this, either C is kind of driven by having a high number of counts, so we have this kind of positive relationship, or it's driven by this idea that we have a wet or wind. So I said if we can match the correlation really, really well, we'll kind of pull it apart and understand kind of what's controlling the framework, which is this idea here, A, B, and C. But I've got these ideas. But we can also take it one step further and think about, well, what does the framework tell us? So we can think about what happens to correlation if we have maybe an infinite number of storms, or if we have more and more storms. So let's say future climate projections said we were going to have more storms in the future. Well, our framework's going to tell us that our correlation is going to tend towards this value, which is the correlation between the mean state of our wind and the mean state of our precipitation. So the focus is shifting to that between year relationship. Then again, this idea of if we have more and more clusterings, if that dispersion statistic got really, really big, we can then have another expression for what the correlation would be. And these top two are kind of a bit kind of confusing, and that's mostly because we've got our Z variable in there and making our maths really yucky. So actually, if we kind of ignore that, we can then think about, well, if it's independent to Z, what's going to happen? So if it's independent to Z and our counts get really, really big, then our correlation relationship goes from thinking about the correlation between our SX and SY, so our aggregate severities, and it actually approaches the correlation between the wind and rain. And equally, which is most surprising, most interesting, if clustering is really, really big, so our storms tend to only occur in those kind of clusters. We have 3 storms in a week, and then nothing, then 4 storms in a week. Then our correlation is going to approach 1. So we have some other kind of applications here. The framework we've focused on storms, it's kind of been designed around thinking about storms, but this is just one kind of combination. So it's just one of many frameworks that we can use, and we can think about this idea of aggregate severity, not just from European windstorms, but from hurricanes, tropical cyclones, compound, dry hot events, anything that's got this idea where we've got an event that brings 2 hazards we can model it with these sorts of frameworks. We don't have to be thinking about a year, we can be thinking about monthly kind of totals. So this gives us a new idea and a new way to approach this problem. We don't even have to think about compound events. We can think about correlation between different locations. And again, we can think kind of get a bit more statsy and think about distribution specific application. So if we know for some reason that a variable follows a specific distribution really well, then we can plug the parameters in, and our framework will give us an exact kind of value of what correlation should or would be. Okay, so let me just wrap up by kind of saying that wind precipitation, aggregate severity, drought storms is negatively correlated when we think about extreme storm. And our framework to model correlation is implied that it's driven by event clustering, the within and the between year variance, but it's that between year variance that's really kind of driving the positive to negative transition. We think more and more about extreme events. And as our framework matches really well, we can think about the theoretical kind of potential limits to correlation, such as approaching one if we have really high clustering. And it just gives us a new approach to understand other hazards, particularly compound events such as windstorms, hurricanes, tropical cyclones. So some of this work has actually already been published in Ireland's Weather. The paper on negative correlation from storms. So you can scan that QR code that will take you there. And also please do, if you like, follow me on Blue Sky and drop me an email afterwards. Thank you very much.
Okay, test my understanding here. I'll try and excuse the sort of non-technical question. I was trying to sort of relate it to see what I want to do. Also, yeah, an idea. So that's good. This framework thinks of that kind of various sensitivity.
Yeah, I just get what you're saying. So in terms of when we're using a percentile-based threshold, so if we're saying it's the 90th percentile, saying that 10% of events at that location are considered extreme. And what that does is yeah, here we go. So this is the 80th and 90th percentiles for wind and precipitation. So maybe the Northern Scotland Southern England transition isn't as clear, but maybe the one that's kind of most identifiable is you can see on the left column there's that kind of ridge, and that is the North Atlantic storm trap where wind speeds are higher. So what the percentile thresholds do is it does mean that you have a location specific threshold is extreme for that location, and the framework will cope with that. The framework just wants the values and it takes the values in and then we'll map. Right. So the severity index idea doesn't necessarily need to happen, but in fact we found that it goes negative when you increase that threshold. The idea behind using the severity indices is to get close to being a measure of loss. So yeah, the framework can account for it, and it does be well, it works anyway.
Any questions in the audience, Gary?
Yeah, and thanks, could we just.
Greg, sorry, Greg, could you share the microphone? Oh, yeah, yes.
Very clear, because your title was the rain. You know, when you start talking about the ASI correlation, you change the percent.
Yeah,
Now, as on most of our storms through the winter month, December, January, February, and the effect of wind and rain can differ as the wind on snow. Are you talking about a water equivalent?
yeah, so I appreciate I've used precipitation rain bit interchangeably. So yeah, when we were our rain data that we were using for rain was rainfall. So we weren't taking into account snow or anything like that. Is that
Well, what this is why we, because most of the storms will have snow in them through the winter months.
yeah?
So.
So I mean, well, I suppose like if you have rainfall. I'm not 100% sure if irrified rainfall. Has a kind of snow component to it. I assume irrified rainfall probably does include first of all. So I suppose technically we are doing it. Yeah, that'd be something I'd have to look into to double check if snow and precipitation kind of how that's related within irrified. But yes, you're right. Most storms are going to come with snow. So different behaviours that I've in Esther not thought about. So yeah, sorry.
And so you're talking about the fact that in the limit is dominated by that between your parents. And you spoke about like potentially that being the constellation. If you think that's I don't kind of get on something you're not thinking about, but is that reasonable expectation or reasonable reasoning behind it?
Yeah, I think and this is something I kind of want to get my head around a little bit more to kind of get a bit more of a clear logical step. My intuition would be that the phase location of the North Atlantic oscillation is going to influence the storm's transition speed. A storm with a high transition speed is likely to have stronger wind speed. A storm with a lower transition speed is going to be over a location for longer. There's more time for rainfall to it. And so I think in effect it's kind of got something to do with that. But because it's kind of more explaining the structure, the correlation, the Dedra is explaining the correlation structure between wind and rain. So it's hard to kind of pinpoint that it is just a North Atlantic oscillation. Storms have been in European windstorms have driven by the North Atlantic oscillation, but there are other factors that play. Scandinavian patterns being one of them as well. So it's hard to kind of pinpoint what it is, but I think that idea that we know that the NAO will influence pathogen be in that particularly in this example of the rain.
Another question on thresholds. So in terms of percentiles chosen, would you expect damage as a loss at 98 percentile event, 90 percentile event, and so how does that relate to sort of financial impacts?
Yeah, that's a really good question. So the our group model I showed right at the start, they used the 98 percentile for wind speed. And that was shown to be really, really well correlated. The 98% of the wind speed is pretty much well used. In terms of an insurance point of view, it would depend on kind of their models, their ideas about what they consider to be damaging. For most of Europe, 98 percentile is kind of high kind of 30s in terms of meters per second, a bit above what that 20 meters per second threshold one would use. So anything kind of 90s and above wind is a good damage threshold. For precipitation, it's very complex. Most studies that have tried to think about kind of damage, haven't used precipitation, flooding damage, they've used river flow. For river flow, they've been using 99.5, 95.9. So I think the best way to think about percentiles is actually more the kind of reverse of the 90th percentile, about 2% of events. So 1 in 50 events is going to cause damage. So yeah, with rainfall, it's hard to kind of know what that perfect one is. Speed of rainfall actually be different percentiles, and that is not something we've considered here, but when we're thinking about our kind of validation plots, if we've then got different percentiles for both of them, suddenly we're going to enter 3D space and get very confused. So yeah, I hope that answers your question. It mostly depends on the individual kind of material that problems, but 90 and above is probably missed out.
Okay, well, in the interest of time, we'll move on to our next speaker. Thanks again so much. Fascinating questions.
Yep.
Thank you very much to see you.
And Lucy, ex-weather impact industrial basic student at Malta. So unfortunately, my case finished at the end of July last year, so apologies if some of the figures are slightly out of date. I'm going to be talking about automated weather impact data collection. So the first thing you probably thought, sort of title was, well, why weather impact data? So I'll be talking about that, and then I'll go on to talk about the global automated weather impact data collection at the Met Office, and then I'll moving on to more specific UK focused weather impact data collection, and talking about current workflow, challenges that we're facing with it, and then the next steps as well. So you probably all recognize warning matrix in the top right corner. And the impact data that we're collecting can be used to help inform this warning matrix. Because imagine, suppose we're talking about like windstorms, imagine you've got 70-mile-an-hour winds in the Outer Hebrides. That might not necessarily need a warning, but if you've got the same in London, it probably would. So this impact data can help us understand when the warning really needs to be issued. So it moves from what the weather will be to what it will do, the impact it's going to cause. As well as being used to be almost helping to generate warnings, they can also use them to verify them afterwards. So where impacts actually felt where we thought they were going to be. The great thing is there's the data out there. Less good is it's really hard to collect manually, especially trying to do it at scale. It's a very laborious process, which is why we need the automated process to do it for us. So this is the overview of the global workflow. We don't need to worry too much about what's in each of the different boxes, but generally it can be summarized with 4 key points. So the first box is all about web scraping. So we use 9 different websites to get the information. So from these websites, we'll get the date, it's got the title, the free text description, and if they've got any tab data statistics, then that's really helpful and we'll collect them too. The next bit box 2 is all about standardizing the data that we have. So for example, some of the impacts we collect from a bushfire or wildfire or a forest fire, and you can see quite quickly how that would really complicate the database if you have all those different types. So we just simplify that. So those 3 would all become wildfire. And then once we standardize the information we've got from the website, we'll then put the free text descriptions through Owie, which is our natural language processor. And that can extract the impact for us from free text. So although as humans, it's really easy for us to see a sentence, 3 people are missing, we would understand that the number of people missing is 3. But the computer would really struggle with that, which is why we need the natural language processor to do it for us. And then the final stage, step 4, that is to basically take what we've got from web scraping, take what Owie generates and merge them together into one impact record into the database. So here's an example. So one Azure is one of the sources that we use. And you can see it's got some tablet statistics. So we'll take them, record them. It's got free text description. So we'll go through that, put it through Owie, the natural language processor, and see can it find anything that we can add to what we've already got. So this example is can. It's got the data for the impacts, so we can add that for the calculations, for instance. And as well as going into our very large CSV file, which is where we store all the impacts in the database, it also goes into a viewer, weather impact viewer. So this contains the impacts for the past 7 days. You can sort them by hazard type. So we want something very similar to this for the UK. As you said, it's easy to see at a quick glance what's been going on there. Because it's got the different colours, well, you can't actually see it here, unfortunately, but all these coloured ones are precipitation related. Well, actually, Chile, where I was doing grey, that's other. And you can see that here it's one event for Brazil. With Brazil for this third event had 3 different records. We group it by it was a 7-day window, and that would be one event. And generally the coverage that we have, then as I said at the start, apologies, this is something old moving out. Generally the coverage is very good. We've got something for I think every country. Indonesia at the time had about 4,000 records, Philippines about 1,000. So you might notice there is a little error with this figure. It's missing like Botswana, Portugal, Belarus. Those do have impacts. I'm not sure why they don't show up, but I promise you there are impacts recorded there. And as I said, we've got something for every country pretty much. Probably noticed the UK adverts, kind of is, it's on records. What if we want a UK database? Why don't we just take those in the UK? That would be great, but for the UK, we want finer scale impacts. So the ones reported here would probably be in storms, which have been very impactful, so they cause like deaths. What we want, well, with your little road flooded, like some random village. I don't know, but there's something powerful because of the extreme wind and cause power lines go down something. So that's what we really want to know. So this is exactly the same diagram as we had before, global database. And I've started in red the bits that we can use for the UK. So we can still, we've got a list of sources, again, websites, we can still get all the information possible from them. Unfortunately though, the sources that we use for the UK are local news sources, and I'm sure you've all read news articles online. They don't helpfully say this is about a flood, this is about a drought. So we can't be standardising because we don't know what the event types are. And then we also can't use OWI for reasons that I'll get onto later. So for the moment, because this is still a prototype work, we get the impacts we can from the websites, and then we just put them straight into the database. So to give you a bit more detail about how this works. So this is our list of sources. It's more than just shown on the screen, but this is where we got them from. That's about 600, so we can use about 400 of these local news sites. And then for each one of these, each day we get a list of what are the new articles that have been added. So you can see that these tend to have the smaller scale impacts that we're after, but not all of them, quite obviously, are weather related. So we use a machine learning pattern classifier to go through and say which one's relevant, which ones aren't relevant. And then for those ones that are relevant, that's when we then go into them. We say the link from the article title, the dates, and the main body text. The date is a bit of a tricky one. Sometimes you can't get that directly from the website. We also record the date that it was scraped, or date that we went through the article. Because that will only ever out by about 24 hours because it's the daily thing. So it's going down seconds, the machine learning classifier. This was about 10,000 words introduced to train the model. And you've got some common words here. There's two relevant titles and not relevant titles. You can see there is some overfitting because near the top of the relevant titles, that's Storm Jocelyn, Storm Isha. but generally it's quite a good classifier. And then for the not relevant titles, that's more words associated with local politics, so like say, will, and council. So those are articles we don't want. And then it's quite a nice graph. This shows all the impacts for May 2024 that we recorded. To get the locations, we use GeoParspy and GeoPy to choose software libraries. So go through the free text again, and say, well, where are the placings that you can identify, and then you take the average of those placings, and that's what gets spot on map. Which is why you have a couple of things in. That's just because the average location wasn't actually online. But as well as this, we can get road names as well, because they're can be quite uniformly written. Princes Street, London Road, you know, we capitalise, or something street, something road, something avenue. So that's a nice bit of just extra information that we can get. Generally, coverage seems pretty good. Got points for Scotland, Wales, England, got quite a lot of points. Kind of obvious one missing, Northern Ireland, have no data points out of May 2024, which quite clearly there should be at least one. Northern Ireland must have had at least one weather impact in May 2024. So this is partly we think because the sources that we have reported in Northern Ireland, there's slightly less of them, and they don't update quite as frequently as England, for example. And the other problem is the place names. So the software tends to struggle a bit more with picking out place names from Northern Ireland compared to like England, that picks out quite well, Scotland that picks out quite well. Also think back to the global impact viewer. It has on the past 7 days, so you can see sort of recent events. So it's similar in the UK to the past 7 days. But first you can select based on the date, and you get the location, building, date again written down, and then also you can get to the article title, so you know roughly what you're going to be looking at before you actually go with stuff. And the really nice thing is, we're actually about 3 or 4 months. So we start March at the end of June last year. So this shows see before it became automated, and then 22nd of April was when we got the process being automated. You can just sort of ignore that bit at the start of May. I broke the code and went away for the weekend, so no impact or reflected over that weekend. But generally, you can see it works quite well. It's putting quite a lot of records. You see, it was very wet start of the year last year, so we're getting a lot the first half and the half pretty much all flooding that's being reported. But you've got that nice little pink red line that's named storm category. And what's great is that we're seeing there's a clear increase in the number of impacts recorded immediately afterwards, which is good because if a storm is named, you're likely to have more impacts associated with it. So it's good that we're getting those impacts. So that's all really positive, but it's not positive is that we've got quite a few challenges. So I mentioned earlier that we can't use ALI for the UK, the mathematical processor. This is because we already know from the global database that it does badly with double counting. We like to repeat ourselves a lot in our news articles. So here's one. There's one road is blocked. But how we will go through it to find 6 different roads being blocked. And obviously that's going to inflate what you can see of the impacts compared to what that impact actually were. And then another point is the impacts that ALI is trained to recognise is buildings destroyed, infrastructure damage, not a match being exposed. So ALI is trained on the really substantial impacts compared to what in comparison it is more small scale norms. So I would definitely struggle with UK, which is why I don't use it. Another challenge, which I hinted at before, was with the software. So it doesn't always get the location right. So those impacts which are on the screen, to be thunderstorm. Yeah, those impacts were Bradford City in these, and it's decided to replace Bradford as being a village in Devon. So if you're looking for impacts of Bradford City, you can think to try and check out random points in Devon. So we know that's another issue. And then also forecast events. These sometimes come through, particularly heat waves, because in this case, and also snow events. Because to try and filter out the spectrum of events, we do a very rudimentary filter, using keywords. So, some examples of keywords would be warning, is maybe someone issue, but not actually have the event yet to feel an impact from it, or set to, like, flooding is set to occur once the rain's actually come through, but it's not yet come through yet, so we can't impact the event has not happened. But the reason that heat waves and snow events in particular come through is because the article says the cold weather is set to continue. So set to is one of our keywords which we say, yeah, it's like speculative, ignore it. Continue is one of the ones that we can say, well, actually, even if it's got words which indicate it might be speculative, we'd like to keep it just in case, because it might be the impacts are set to continue. Well, okay, but what are the impacts that we're continuing on from? So we keep it just in case, but does mean that those events can slip through. And another point is kind of linking to this one. We get forecast events, we also get historic events mentioned sometimes. So 10 years on from, or like remembering 10 years ago today, this event happened, these impacts were felt. That's great for an archive, but that's not what we're going to be. We're going to be assuming that those events happen on the day of this report, which obviously it's not, it's happened 10 years ago. So we know that that's something as well to do have a look. So I guess the only point of next steps is fix all the stuff we just mentioned we've had challenges with. So making the UK version of ALI, one to deal with the smallest, like fine scale impacts, and hopefully won't, as we've got 6 roads closed when it's only 1. We may need to improve the location finding, and for filtering out speculation of forecasts, warnings. We could probably use machine learning to try and do that for us. That would probably be a better approach than just a quick, these are some keywords that have yes or no. And then obviously there's a lot more things that we can take us a lot further. It's a lot more detail we can put into it, that we can grade that archive. Use pictures to provide more detail so that people are then going in to look at it. You can run it in maybe near to real time. The script only takes like 10 minutes to run. There's a lot more to do. It's sadly I no longer work with it, but it's really still really exciting stuff going on. Any questions?
Yes. My team's involved in the manual collection. So I can say this is very useful overview. I've got a couple of questions, if that's okay. Can it make any estimate of the sort of scale of the impacts? Sort of like the matrix at the beginning, and get back to the categories.
At the moment, we're not getting into scenario. I suspect before we even get on to thinking about that, we need to get the UK version of our national language testing. We need to get that sort of start with so we can get statistics associated with these events, and then from there we'll then be able to go well. Then maybe put their pressures big. So if it's under this, it's not very happy that it's over this, it's more severe. But that's probably quite a long way out of what to do.
second question, that's okay, is. So Lawrence, is this exclusively sort of traditional media? Is this like social media?
No, it doesn't, so at the moment it is purely newspaper articles for the UK, and then for global, it's more humanitarian websites and a couple of like more news-based sources.
Okay, because so that really shows what the big issue is the gaps in the data with social media. They create a little bit. It would be a huge job to transfer to social media as well.
I think one thing that we found in social media is obviously people like to embed the impact that happened. Well, that was huge flooding, or there's a flood before that, something like that. So I think there has been some research into using well, X, formerly Twitter. I think there's been some people looking into that to get impacts, but not anything that I've been. Yeah.
Thank you, questions. I'll open to the floor. Alice, your question or someone?
No, it's not like, it's my question.
Yeah.
I can, if you want to repeat it, that's fine. Yeah, it just kind of follows on a little bit from what you said about social media, and how do you deal with, say, clickbait articles, which goes through sort of traditional news, but you might find one newspaper reports it in a sort of more scientific way, and another one exaggerates it. So how do you deal with that?
How to reduce those related impact, because as much as you can phrase it like it's been the world's biggest disaster, if your statistics still only list one power cut for 30 minutes, that you can't really inflate that much. So I hope that statistics will help reduce that a bit more. But there have definitely, I've seen the articles where it's like 100-mile wall of snow across the country, and we've also seen those sorts of articles. Those ones do tend to get picked up by the filter expected events. So those ones we normally can disregard immediately, but yeah, that's something they're aware of.
So, on top of like event attribution, like finding them, have you considered grading? Because obviously, grading is kind of down in medium, but like it's still a major source of news for foreclosures, like offline in real time. It's like given kind of natural language processing has increased in accuracy over the last couple of years, do you think doing that in real time would be a viable route to mapping these events and closures?
I think it could. But very close to report, they normally get reported online as well, so we can use vehicle not vehicle traffic, but mobility data and things like that. So I'll probably do a very similar job, so I'm not sure if we were just having both of them on top of each other. But it's certainly something that could be done, could look at gradient.
You remember on the last one, the internet caption?
Yeah.
Was that data that's you quality control and then it's feedback again to see the
Yeah, that's all sort of the future still, work, but it would be sort of being able to look at the news articles from maybe 5 years ago, I think. Because at the moment, the news articles they only go back a certain amount of time. So I think the earliest record we have was end of 2023. Most of the articles before that they're regulated or things like that. So the internet will help us get that data in archive. But it still be, we still have to go through the checking.
You. Well, a quick round of applause to both our speakers. Thank you both very much for coming with visitors and your fascinating talks, and hope you enjoy yourself. See you. So that's us for tonight. As I said, our next meeting is actually in Aberdeen. Maybe see some of you there in person, but it'll be online as well. Other than that, wish you all a nice evening.